Welcome back to the Deep Dive. And hey, if you're joining us from the energy world, a big welcome to the Third Way Energy podcast as well.
Great to be here.
Today, we are really diving deep, exploring some, amazing hybridization opportunities in energy.
Specifically focusing on something many people just overlook completely.
Exactly. We're talking about agricultural waste.
Hmm.
The stuff left over after harvest. Could it actually power our world?
It sounds almost too simple, right? Like, really? Dead plants.
Huh. Yeah, my first thought too. But stick with us because, honestly, you are in for a surprise. Let's unpack this whole thing.
Definitely. I remember hearing about that Nigerian factory owner.
Oh, right. The story about him asking if agricultural waste could genuinely replace his diesel boilers, especially with those crazy fuel prices.
And the short answer we found in our sources was a pretty clear yes.
A resounding yes, actually. But the long answer. That's where it gets really interesting.
That's what today is all about, because it's not just that it works, but how and why it's so compelling.
Exactly. We want to give you that long answer today, the science, the tech behind it, the money side of things.
So you really get how these, dead plants become serious energy and why it's such a potential game changer.
Especially for places like the Global South, right?
Absolutely. But don't worry, we're not going to give you a thermodynamics lecture.
Promise?
Promise.
Good.
Just the real why behind the what, how this stuff actually becomes power.
Okay, good. So for anyone listening who's maybe short on time, needs the elevator pitch.
Yeah.
Let's do the 60-second version first. What's the absolute bottom line?
All right, the quick version. Agricultural waste can replace things like diesel and coal boilers, no question.
And the cost.
That's the kicker. Often at something like 30 to 50% lower cost.
Wait, 30 to 50% cheaper?
Yeah. It's a huge saving. And the tech, it's proven it works. We're talking solid economics.
Like actual numbers?
Yeah.
Payback periods?
Typical paybacks are in the 3 to 7 year range. And the IRRs, the internal rates of return, often between 15 and 35%. Pretty attractive.
15 to 35% IRR. That's really good for this kind of infrastructure project.
It is. And we're already seeing big players, manufacturers in Africa, in Asia, running their factories on biomass.
Using what kind of stuff?
Things like rice husks, sugarcane waste bagasse, they call it. And they're cutting their energy bills by 20, sometimes 35%.
So that quote we saw, if you're buying fossil fuels for process heat while sitting next to crop waste, you're literally burning money.
It's blunt, but it's basically true. You're throwing money away.
And there was that key number, right? The threshold.
Yes. The rule of thumb is if you can get that biomass delivered to your site for less than 30% of what you currently spend on energy, then the project will work, period. It's that clear cut in many cases.
Okay, will work, period. That's a strong statement. What really stands out there is that this isn't some lab experiment.
Not at all. It's de-risked. It's bankable. People are doing it right now successfully. It's real.
It's real. Okay, so to get why it's so real, maybe we should back up a tiny bit. The fundamentals. What is biomass energy, actually? How does it hold energy?
Right. Basics first. Biomass energy is just using organic stuff, mostly agricultural waste, like we said, as fuel.
And you had a great analogy, like solar energy.
Yeah. Think of it as solar energy in solid form. Plants use photosynthesis, right? They take sunlight, CO2, water.
And make sugars build themselves up.
Exactly. They build cellulose, hemicellulose, lignin, the plant structure. That is stored solar energy. When we use biomass for energy, we're just releasing that stored sun power.
Simple when you put it like that.
Yeah.
And that ties into the whole carbon thing, doesn't it? Carbon neutrality.
It does, directly. When you burn or convert biomass, the CO2 released is pretty much the same amount the plant sucked out of the air while it was growing.
So it's a cycle. Unlike digging up ancient carbon with fossil fuels.
Precisely. It's a closed carbon cycle that makes it fundamentally renewable in a way fossil fuels just aren't. It's a huge difference for the planet, obviously.
And the sheer amount of this stuff, the raw material, it's mind-blowing.
Oh, the scale is unbelievable. Globally, agriculture produces something like 5 billion tons of these residues every single year.
5 billion tons. Can you put that in energy terms?
Easily. That contains roughly 80 exajoules of energy. An exajoule is a lot of energy.
How much compared to, say, global use?
It's equivalent to about 13% of total global energy consumption, just from agricultural leftovers.
13%? Wow. And what kind of leftovers are we talking about mainly?
Well, you've got massive amounts of wheat straw, maybe 850 million tons a year. Rice straw, about 730 million tons. Corn stalks, maize stover, 1.4 billion tons.
A billion, just from corn.
Yeah, then sugarcane bagadas, nearly 500 million tons. Plus rice husks, cotton stalks, palm residues, even cassava peels. The list goes on, it's everywhere.
The scale is just, yeah, hard to grasp. But it's not just how much there is, right? It's what it's made of that matters for energy.
Exactly. It's complex stuff. You've got the main structural parts,
Yeah.
cellulose and hemicellulose, making up maybe 55 to 85%. Then lignin, which is like the plant's glue.
Okay.
Then smaller bits like oils, proteins, extractives, and minerals, which become ash when you burn it.
And you mentioned two big enemies for efficiency.
Yes. Enemy number one. Moisture.
Uh-huh.
Water content can be anywhere from 10 to 60%. All that water has to be boiled off before you get useful energy. It just sucks heat away.
Right, wasted energy just drying it.
Yeah.
And the other enemy?
Ash. Specifically the type of ash. Some ash, like from rice husks, has lots of silica, high melting point, usually okay. But other ash, say from certain straws, can be high in potassium, and that stuff can melt at lower temperatures, forming sticky, glassy clumps called clinkers.
Clinkers. Sounds bad.
Oh, they're terrible. They can block up equipment, force shutdowns, a real operational headache. So ash chemistry matters a lot.
Okay, so we have this huge amount of variable stuff, wet, dry, different ash. How do we actually turn it into useful energy? You said it's like high-tech cooking.
Huh? Yeah, kind of. There are basically four main ways, four thermochemical recipes to get the energy out.
Let's cook. What's recipe number one?
The oldest one. Combustion. Simple burning. Just add enough air and light it up.
Like a campfire, but more control.
Exactly, but way more efficient in modern systems. It happens in stages. Drawing the water off first, then gases, volatiles release and burn. That's the flame you see. Finally, the solid char burns.
And the efficiency.
Modern boilers can hit 85 to 92% thermal efficiency. Really good at just getting heat out.
Okay, simple burning. What's next?
Number two is gasification. This is more like chemical magic. Instead of full burning, you deliberately limit the oxygen.
Limit oxygen. Why?
Because instead of just getting heat and CO2, you convert the solid biomass into a combustible gas called syngas.
Syngas. What's in that?
It's mainly carbon monoxide, CO, and hydrogen, H, with some methane, CH. It's a fuel gas itself. You can burn it for heat or use it in engines or even make chemicals. Very flexible.
Ah, okay. So not just heat, but a fuel product.
Yeah.
Interesting. Recipe three.
Pyrolysis. This one is all about heat, but with no oxygen present at all.
No oxygen. What happens then?
The biomass breaks down differently. It produces char, some non-condensable gases, and importantly, a liquid called bio-oil. Fast pyrolysis pushes conditions to maximize that oil.
Bio-oil. So like a renewable diesel substitute.
Well, that's the dream, but this bio-oil, it's tricky stuff. Some call it Satan's chemistry.
Uh-oh. Why?
It's incredibly complex, over 300 compounds. It has lower energy than diesel, lots of water usually. It's acidic, like pH 2.5, think vinegar, and it's unstable. It can thicken or polymerize over time.
That's easy to use.
It requires significant upgrading, refining. It's not a simple drop-in fuel replacement generally. The chemistry is quite hostile.
Okay, noted. Satan's chemistry. What's the last recipe? Number four.
Torrefaction. This one's a bit different. Think of it as mild pyrolysis or maybe biomass roasting.
Roasting, like coffee beans.
Sort of. You heat it moderately, 200, 300 degrees C, again without oxygen. The goal isn't full conversion, but to improve the biomass itself as a fuel.
How does it improve it?
It drives off moisture and some volatiles. The result is a product that's much more energy dense, almost like coal. It repels water, reduces moisture uptake by 80%, so it stores better.
Less water, more energy packed in.
Exactly. And it becomes brittle, so it needs way less energy to grind it up, like 70, 90% less grinding energy. Makes it uniform, easy to handle.
So it's more about pre-processing the fuel, making it better for other uses.
Precisely. You lose a bit of mass, maybe 30%, but you keep about 90% of the original energy in a much better, more storable form factor. It's a game changer for logistics and handling.
Fascinating. Combustion, gasification, pyrolysis, torrefaction. Okay, so we know the what. Now the how, the machines that actually do this stuff, especially for gasification, you mentioned different types.
Right, the hardware matters. For gasification, their reactor design is key. You've got fixed bed gasifiers first.
Fixed bed, meaning the fuel just sits there.
Pretty much. Two main types. Upgraft is simple, very reliable, but it produces a lot of tar.
Tar again. The sticky stuff.
Yeah, 50, 100 grams per cubic meter. So updraft is mostly good for direct heating, where you just burn the tar along with the gas.
Okay. What's the other fixed bed?
Downdraft. Here, the gas flows down through the hot char bed. This cracks a lot of the tar, so you get much cleaner gas.
Cleaner gas is better for?
Engines, much better for running engines to make electricity. But downdraft gasifiers are typically smaller scale, usually less than 5 megawatts.
Got it. What comes after fixed beds?
Fluidized bed gasifiers. These are pretty clever. You blow gas up through the biomass particles fast enough that they kind of float and mix like a boiling fluid.
Like bubbling sand.
Exactly like that. You have bubbling fluidized beds, BFB, and circulating fluidized beds, CFB. The big advantage is fantastic mixing and temperature control.
Why is that so important?
Prevents hot spots, handles variations in fuel really well, and crucially, keeps the temperature even to stop that ash from melting and forming those nasty clinkers.
Avoids the clinker problem. And scale.
They scale up well, typically 5 to 100 megawatts. Very versatile.
Okay, what about really big scale, like power plant size?
Then you're looking at end-train flow gasifiers. These are beasts. Very high temperatures, 1200 to 1500 Celsius.
Whoa.
You need finely ground biomass, injected with oxygen or steam. You get almost complete conversion and basically tar-free syngas. Ideal for large scale, over 100 megawatts.
Sounds perfect, but what's the catch?
High cost. You need special materials for those temperatures, lots of energy for grinding the fuel really fine, and they use a lot of oxygen, which adds cost.
Trade-offs, always trade-offs. Is there anything even more high-tech?
There is. Plasma gasification. Uses electric arcs, like lightning bolts, to get temperatures over 3,000 degrees C.
3,000 degrees?
Yep, it obliterates everything. Total conversion turns ash into a harmless glassy slag. Great for hazardous waste because it destroys toxins and locks up heavy metals.
But for regular farm waste?
Probably overkill. It uses a lot of electricity to run the plasma torches and the electrodes wear out. So economically, it's usually tough to justify just for biomass energy value. More niche.
Makes sense. So across these methods, especially gasification, you mentioned tar several times. You even hinted at Satan's chemistry. Is tar the big villain here?
It really can be, yeah. Tar is just this horrible, sticky, complex goo of heavy organic compounds that condense out as the gas cools.
And it causes problems how?
Oh, it clogs everything.
Yeah.
Pipes, valves, filters. If you try to run an engine on terry gas, it fouls it up quickly.
Right.
If you want to use catalysts for chemical synthesis, tar poisons them. It's a nightmare.
So managing tar is critical.
Absolutely essential if you want to do anything more than just simple burning of the raw gas. There are ways optimizing the gasifier itself, cracking the tar downstream with heat or catalysts, physically scrubbing it out, but it adds complexity and cost.
Okay, so we've got the science, the tech, the potential pitfalls like tar. Let's bring it back to the listener. What does this actually mean for energy systems? Where do these processes fit? This is the hybridization part, right?
Exactly. This is where it gets really practical and exciting. The hybridization opportunities are huge. Let's start with power generation.
Okay, making electricity.
The most common route for smaller scale, say 10 kilowatts up to 5 megawatts, is using internal combustion engines, like modified diesel or gas engines.
Running on the syngas.
Yep, running on that producer gas from the gasifier. It's proven tech, gets you maybe 25–42% electrical efficiency. But you need fairly clean gas, low tar, low particles.
What about bigger scale power?
Gas turbines offer higher efficiency, lower emissions. Think jet engines adapted for power generation, but they are very picky about gas quality. Need exceptionally clean gas, almost zero tar.
So more complex gas cleaning needed there.
Definitely. The other main route, especially reliable, is using a biomass boiler to make steam, then running a steam turbine.
Like a traditional power plant, but fueled by biomass.
Exactly. It's less efficient, maybe 15–25% at small scale, up to 30–35% for larger systems, but it's robust and can handle less clean fuel, even direct combustion.
Okay, power generation. What about using the heat directly in industry?
This is often the easiest win, as you said. Steam generation for industrial processes. Just replacing a fossil fuel boiler with a biomass boiler.
Direct swap.
Pretty much, or retrofitting existing ones. You get that 85–92% thermal efficiency, direct cost savings on fuel. Huge market.
Makes sense. What about using both heat and power?
That's combined heat and power, CHP, or cogeneration. Super efficient. You generate electricity and capture the waste heat to make steam or hot water for the factory.
Total efficiency must be high then.
Oh, yeah. You can push 75–85% total system efficiency if you have a good match between your heat and power needs. Really maximizes the energy value.
And you mentioned cooling. using heat to make cold.
Yes. Using absorption chillers, these devices use waste heat from CHP or direct heat from biomass to drive a refrigeration cycle.
So you can use waste heat for air conditioning or process cooling.
Exactly. Think food processing plants, cold storage, places needing refrigeration. It adds another layer of value, turning waste heat into useful cooling. Single effect chillers use hot water. Double effect use higher temp steam for better efficiency.
Very cool, literally. Okay, beyond heat and power, what about making stuff, chemicals?
Absolutely. This is the biorefinery concept that syngas from gasification. It's CO and H. That's feedstock for making methanol, ammonia, even synthetic diesel through the Fischer-Tropsch process.
Wow, turning waste into liquid fuels or fertilizers.
Precisely. And you can also produce high-purity hydrogen from syngas, potentially for $2 to $4 per kilogram, which is very competitive, especially for green hydrogen targets.
So waste becomes valuable chemicals. What about fitting into the bigger energy picture? The grid, renewables.
This is a critical point. Biomass offers something wind and solar often struggle with: controllable, dispatchable power.
Meaning you can turn it on and off when needed.
Exactly. Wind blows when it blows, sun shines when it shines. Biomass plants can ramp up or down to meet demand, providing stability to the grid. That's huge for balancing renewables.
So they can work together. Hybrid systems.
Perfect combination. Studies show adding just 20–30% biomass capacity can effectively firm up intermittent wind and solar, making the whole system much more reliable. It provides that baseload or flexible power needed.
And the biomass itself is stored energy, right?
Yes, especially if you pre-process it using torrefaction or pelletization. You create an energy-dense, stable fuel that can be stored and used whenever needed. It is a form of energy storage.
What about off-grid situations, remote areas?
Ideal for microgrids. A biomass gasifier or CHP unit can be the anchor for a local grid, providing stable power 247, allowing high penetration of solar or wind for remote communities or industrial sites, energy access, and renewables.
Okay, the applications are incredibly broad. Power, heat, cooling, chemicals, grid stability. But the big question remains, does it actually make financial sense? What about the environment?
Let's hit economics first. Capital costs, the upfront investment, definitely have economies of scale. Smaller systems under a megawatt might be $800, $1,200 per kilowatt installed.
And bigger ones.
Go up to 10 megawatts or more, and that cost can drop to $400, $600 per kilowatt. Big difference. But remember, the balance of plant pipes, controls, building, and development costs add up too.
But overall, the project economics you mentioned earlier sound good.
They typically are. That 15–35% IRR and 3–7 year payback is based on real projects. The key sensitivities are always: keep the plant running reliably, high capacity factor over 85%.
And the feedstock costs.
Keep that feedstock cost below 30% of your energy revenue. And obviously, the price you get paid for the energy matters.
Are there new ways to finance these? Not everyone has millions up front.
Yes. The energy as a service model is growing. A developer builds, owns, and operates the plant, and the customer just signs a long-term contract to buy the heat or power. Takes the capital risk off the customer.
Makes it much easier to adopt. Okay, what about the environmental side? Is it truly green?
If the biomass is sourced sustainably, meaning using residues, not cutting down forests for fuel, then yes, it's broadly carbon neutral, like we discussed. That's a major plus.
What about the ash leftover? Is that a waste problem?
Not necessarily. That ash can be a valuable product. It's rich in potassium K, phosphorus P, calcium Ca, great as fertilizer or soil conditioner.
So back to the farm it came from.
Often, yes. Or the silica in rice husk ash can be used in making high-performance concrete or even ceramics. Its value can range from $20 to $200 per ton. Turns a cost into revenue.
Okay, good economics, good environmental profile. So why isn't every factory near a farm running on biomass? What makes these projects succeed or fail?
Great question. We looked at data from over 200 projects, and clear patterns emerge.
What definitely works?
Captive feedstock, having your fuel source nearby, ideally less than 250 kilometers away, running the plant consistently, baseload operation over 7,000 hours a year, and crucially, professional operations and maintenance, O&M.
Professional O&M. Why is that so key?
Because these aren't set it and forget it like solar panels. They are thermal and chemical plants. They need skilled operators, regular maintenance. Things go wrong if you don't have that.
Okay, so what kills projects?
Feedstock having to travel more than 250 kilometers. Transport costs just eat the margins. Relying on seasonal supply without building up a big enough buffer stock. Not having a guaranteed buyer for the energy. A long-term offtake agreement.
And the O&M again.
Untrained O&M is a huge failure point. And finally, picking the wrong technology for the specific fuel you have or the energy you need, that tech use mismatch can doom a project from the start.
So getting the feedstock logistics, the operations, and the contracts right is absolutely vital.
Absolutely critical.
All right, so wrapping this all up, what's the big picture here? What should people take away from this deep dive?
I think the main thing is that biomass energy, especially using agricultural waste, isn't some far-off dream. It's here. It's now.
It's mature tech, it's profitable.
Exactly. It works today, particularly for industrial heat and for distributed power, especially in agricultural areas where the fuel is right there. These hybridization opportunities are real.
Yeah, the science is done, the tech proven, the economics make sense.
And the environmental case is strong. So the real question isn't if it can work. It's more about how fast can you make it work for your situation.
And maybe, how do you lock in that local feedstock supply before your competitor down the road does?
That's becoming a real factor, yes. Securing supply is key.
It really does make you think, doesn't it? If you are surrounded by this potential fuel source, this agricultural waste, and you're still burning fossil fuels.
You are quite literally burning money and missing out on efficiency and sustainability gains.
But maybe the final thought for everyone listening is, beyond just farm waste, what other overlooked resources, what hidden energy potential might you be sitting on?
What opportunities for hybridization, for smarter energy use are right under your nose, just waiting?
Something to ponder. That's it for this deep dive. Thanks so much for walking us through that.
My pleasure. Fascinating topic.
And thank you all for joining us. We look forward to the next one.